Okay, I'm back. Sorry for the background, but everything is now okay. All right. So I was to discuss on the standard error, and so standard error from the term that is error, it's basically a deviation here. Okay, so we are trying to that is to find the deviation between what, between maybe the actual value, okay, and the mean. Okay, so we usually have that's how basically we define that is a standard error. But we under standard error we usually have many type maybe errors, okay, or some of, what can I call them, subcategories of standard error. Like for example, we can have what we call SEM, that is the standard error of what, or of the mean. Okay, and also we also have another one called standard error of estimate, that is C. Okay, you can maybe try and check more on that is the difference between those subcategories. Okay, but basically what what standard error shows, shows basically the deviation of it's like we can call it a deviation of a standard deviation. Why? Because from even from its formula, let me try to that is come up with somewhere I can illustrate, like even from its that is even from its formula, that is, it is denoted as standard error. It's given by variance. Remember, what is S? What did we call S? Remember we talked about S squared and S. What is S squared? If you can all recall, what is S squared?
Good evening.
Good evening.
It's the sample variance.
Yes. So S squared is the sample variance, meaning S, what will be S? S will be what? S
The
will,
standard
will
deviation.
be now the data standard deviation. Okay. The reason and remember I had already said that um, we usually say, okay, standard error, it's kind of deviation from a standard deviation. That's why we usually compute standard error in by what, using this formula, that is standard deviation divided by the square root of the sample size. Okay, like we are deviating the standard deviation, okay, of that sample, or of the that is of that sample data. Okay, so basically what we are saying here, standard error, it's like now the deviation, because under this is variance, this is variance, this is variance. So um from the term variance, remember variance, we said it is what, deviation, and it is deviation that is from what, from the mean. Why? Because let's assume we have a data sample with what, with these values like x1 comma x2 x3 up to xn. Okay, for us now to get deviation, that is variance, we usually what, we usually square that is the difference, or do a summation of the difference between the individual values and the what, and the mean. Okay, like for example, if we calculate the mean of this data set, we'll get what? We'll get x bar as what? As the mean. That's why variance, we usually say it is summation of what? Summation of xi's, okay, minus that is x bar. Check now, here it is the deviation we are talking of. The deviation of our data points, that is from the what? From the mean, okay? Then you square to make the value to be what? An absolute value. And then you divide by n minus 1, okay? So this is variance. And here, the variance is showing us the what? The deviation. Okay, so the standard error, it is that standard deviation, okay, between what? Between the values and the what? And the between the values and their mean, or it is the deviation, or what can, yes, let me use deviation. It is the deviation of values away from the what? Away from the mean. Okay, so basically that's how I can define what? Standard deviation. All right, so like if I see a standard error, which is what? Which is a big value, then I know that is our what? Our values are far away from the what? From the mean. Okay, and this might be a result of maybe outliers in our data set. Okay, and if we have outliers in data set, then definitely we won't get the best what? We won't get the best model. So what I can maybe conclude on the standard deviation definition, um, that is, the smaller the standard error value, okay, the better the what? The distribution. Why? Because if we have small value of the, that is, of the standard error, then it means that is our values are close to the what? Are close to the mean. It's like the error term, okay? The error term, when we are discussing about what? Maybe the error time. Let's say this is the line of best fit. Then we have what? We have that is that some data points. Okay, some data points. So the error term, remember, we defined it as the vertical deviations. Okay, so that is the distance between this data point and the what? And the line of best fit. Okay, this is we call the error term. Okay, we call this the error term, or the what? The y deviation, or vertical deviation, if we can use the best term, vertical deviation, or the residuals. Okay, so if maybe that is or the closer the data points to the line of best fit, okay, the better also the model. Okay, then the far, or the that is, the larger the distance between the data points and the regression line, then we'll also get what? We'll get also a poor that is a poor um, model. Okay, we'll get a poor model. Okay, so basically that's how I can define the standard error. Okay, and in case maybe it's not clear, we can go and research more. Okay, that's all right, Samuel. Hello.
Yeah, yeah, hello, yeah, that's fine, that's fine.
Okay, okay, that's okay. So I want us now to discuss about that is the the other that is the other uh, part of our analysis, and it is the analysis of what? um, Analysis of analysis of variance. Okay, analysis of variance. So under analysis of variance, I've said we are going to discuss that is the degrees of freedom. Okay, I will also discuss about sum of squares, but for the sum of square, I think most of you have come across the sum of squares method, because that's what we've been doing when we were performing that is the variance. Okay, manually. And also, we've also discussed about the mean square. Okay, the mean square. Remember when we are talking about the cost function. Okay, I indicated the formula for what? I indicated the formula for that is mean square error, and we said it is one of what? It is also a good measure for that is for a model, for accuracy of a model. Okay, so basically the degrees of freedom, um, and mostly you will find or you will get degrees of freedom. More so we'll discuss about the degrees of freedom when we will be dealing with the distributions. Okay, like the chi-square and the t-distribution. Okay, there it's where we have a broad discussion of that is degrees of freedom. But for now, I can define degrees of freedom as that is I don't want to say it is a statistic. Okay, I don't want to say it is a statistic, but basically it is a number or a value which we usually use to that is to measure independency or to indicate independency in what? In that is in our data. Okay, and the way we usually calculate the degrees of freedom is that we usually subtract the number of relations from the that is from the number of observations. Like for example, if we are dealing or if we want to determine a degree of freedom, maybe for a sample data, then we usually take that is the total number of observations and then deduct 1. That is n minus what? N minus 1 for us to get that is the degrees of freedom. And from even the example, you can see we have a total number of that is degrees of freedom 23. Okay, whereby it is now the n minus what? Minus 1. That's how we usually get the degree of freedom. That is n minus 1. It's mostly the degrees of freedom. Then we have the sum of squared, that is sum of squared. Under sum of squared, we usually say the smaller, okay, the smaller the residual value, okay, that is the better the model. If the residual value is less than what? Is less than the regression value, that is sum of squared, then we usually say also your model it's good and yes, it's a reliable. Then we have that is the mean square or the mean square error. But no, I don't want to include the that is the error. But the mean square, of course, it is the mean of sum squared. And then we have the F significance. This is the very important point to focus when now dealing with what? With this kind of analysis. Okay, like this value, we usually say that we usually compare this F significance value with what we call p-value. Okay, and p-value is majorly used as a benchmark to show that is the reliability of a model. If our model is what, it's reliable enough, maybe for use, or maybe if it is a predictive model, how it is reliable, that is for prediction. Okay, so if we usually say that if the F statistic, okay, sorry, if the F significance don't it always confuses, that is the F statistic and the F significance. So if the F significance, or the significance F, is less than 5% or less than 0.05, basically 0.05, it is 5%. If it is less than 0.05, then we usually say that your model is reliable. Why? Because it is statistically significant. Okay. Otherwise, if your value is greater than 5% or greater than 0.05, then we usually say your model is unreliable, or it is statistically what? Insignificant. Let me go through that is the notes which I prepared, that is as a guideline for the ANOVA analysis. So that is the analysis of variance. So basically, it splits the sum of squares into individual components that give information about what? The level of variability within the regression model. And we've talked about that is df, which is the number of degrees of freedom associated with the what? With the source of the variance. And we've said for this case, the degrees of freedom is given by observation minus what? That is minus 1. Okay, observation minus what? Minus 1. That's when we get that is the degrees of freedom. Like for example, if we were to say to compute the chi-square, okay, the chi-square of what? The chi-square of this data, then we'll say this data is as a chi-square distribution with the degrees of freedom, that is n minus 1, which will mean that it has that is a degrees that is degree of freedom of 24 minus what? Minus 1, which is 23. Then we have sum of squared. So we usually say that the smaller this that is the residual compared to the total sum of the squares, the better the model fits what? Fits your data. Okay, that is the smaller this value is, okay, compared to this, then the what? The better your model fits the data. Then we have mean square. We've said this is the mean square, and this is so basic. Then we have F statistic. Okay, and F statistic, we've said it is a F test for the null hypothesis. We maybe you will learn because I won't discuss about F statistics and student T distribution. Maybe you can go and try and check something on the same. It is an advanced level, but knowledge is power. You can go and check that is something about what? Something about um, F distribution and student T distribution. Okay, so we are here under significance F. So significance F is the what? Is the p-value of F. So the ANOVA part is rarely used in a simple linear regression analysis in Excel, but you can definitely go and check more on that. But what it means, that is the significant F value gives an idea of how reliable or statistically significant are your what? Are your results. Like for example, if significance F is less than 0.5, which is 5%, then your model is what? It's okay and it can be reliable. Okay, but if the that is the greater, if the that is your significant F is greater than 0.05, then probably you will need to do what? You'll need to choose another independent variable. Okay. Yes. So basically on this ANOVA or analysis of variance, we basically focus on the what? On the significance F, because that's what we can use to infer or to make some decisions about the model. So if your model is good, okay, or it's okay, then you will find that of course the um, the r square value will be okay, or meaning it will be more than 90%. Okay. Also, your standard error will be small, that is smaller. Okay. And then your significance F will be less than what? 5%. If all those aspects or factors are okay, then your model will be what? Will be also okay. Then you can go and read more on the multiple R on the notes. I've just summarized everything. Okay, I've just summarized everything. All right. So now let's come to the that is the regression analysis part. And I had explained here and this one, and the major or the main point of focus, it's what? It's the coefficients. Because if we get the coefficients, then we will have what? We will have our linear equation, linear regression equation, and that will be what? That will be our model. Like for example, in our model, that is, we wanted to predict the what? The y, which is the umbrella cells, depend or using the rainfall amount and the yes, using in fact using rainfall amount. So for that we had to find the coefficient of x, which is the rainfall coefficient, and then also the intercept. And you can see from the data we have the two that is the value, the two values, that is the x variable and the intercept. And with that, we can now come up with the model. That is, y is equal to 0.4482 minus 18 point what? 0.91. So that's how we come up with the model. I had already discussed this. We even did a prediction. Remember, we also did a prediction whereby we remember when we were talking about, maybe we cross confirmed with what? With the trend formula and forecast what? Forecast linear. Okay, or when we used the forecast formula. All right, so I think up to that point, we've already that is exhausted the second method. So I think now this is also the first that is method we used. This is the first method we used, and the good thing, I have illustrated all the steps very well. Okay, I've illustrated all the points very well, so it shouldn't be hard for you to follow up. Okay, so I want us now to discuss about the last method. Okay, and then we can, once we are done, we can call that topic, that is as done. Okay, yes. So after that, now tomorrow we shall start with the most last topic, which is now the distribution and hypothesis testing. Distribution and hypothesis testing. So now in Excel, we have some inbuilt functions which we can what? We can compute, that is the linear regression. We have slope. Why? Because we'll need the gradient of all the constant for x variable, which we said it's always our slope. And then we also have another formula for what? For the intercept. Okay, if you want correlation, I also showed you about the Corel formula when we were doing practicals on covariance and correlation. Then we have that is linest. Okay, linest function, and for this function, basically it gives us, or it uses the least squares regression method to calculate, that is the values which best explains the relationship between what? Between two, that is variables, and it always returns that is two values, that is the value for the intercept, and and the value for the slope. Okay, yes. And then after that, we'll now come to calculate maybe the slope and the what? And the intercept separately. Okay, so now we are going to do that is example on that, or the practical part on that. So take note of that and maybe pay attention. It's very, very, very easy. So let me undo that. No, I can do away with that. So first of all, remember in our model, what do we need? We need the constant or coefficient, that is coefficient of x variable, x variable. Okay, and then we need what? We need the y intercept. Okay, so these are the two major values we need, and we have some formulas which we can use to come up with what? With the constants. Remember here, what we need for us to build the equation of a straight line, or the equation of a linear regression, it's what? It's this value. Coefficient, that is the coefficient of x and the y-intercept. And we shall get what? Such equation, linear regression equation. So we've said we can use individual formulas, that is and um, slope and intercept formulas, and we can also use what? Line set. Okay, okay, that is formula. Okay, so let's start with the first one. I've said this one will return what? This one will return uh, two values, that is the slope and the y-intercept value. So with that, we are going to say it is equal to that is line nests, and you can see returns statistics that describe the linear trade matching that is matching on data points. Okay, by fitting a straight line using the what, the least square method. So we are going to use that. Then here now we need what, we need the non y's and the non x's, and we have them here because this is will be our non y values, then comma non what, non non x what, x values. So after that, once you run, you'll get what, you'll get two values. And remember, these values are the ones which we've been what, we've been getting, or we can just reconfirm these values. Okay, let me reconfirm these values, paste here, and you can see this value, it's the same as this, is the same as this, and this value, it is the same as this. So we've received, or we've gotten the same what, the same output. So for that is lines, it's a so basic formula for you to get maybe the that is the constants in a very easy and fast way. Then we can now find maybe the individual. Well, remember, this is what? Now this is the slope, and this is what? The intercept. This is the intercept. Okay. But now we can calculate the coefficient and the intercept using individual formulas. Like maybe let's start with the what? With the slope. So with the slope, we are going to use the slope method. Okay, we have the slope method, and for the slope we'll also need the non what, the non y's and the non x's. So it will be I will highlight the non y's and then go to the non what, to the non x's. And the good thing, the formula itself will guide you. Okay, provided you define your what, your variables. So with that, once we run, you can see we've received the same value of the what, of the slope. So you can see these are the what, this is the same value. What about the intercept? What about the intercept? So under the intercept, we are going to use the intercept function. So we have the intercept function, and for the intercept function, you can see it calculates the point at which a fine a line will intersect the y-axis by using a best fit regression line plotted through the non-x values and y's, that is, and the y values. So with that, we can just use now the intercept, and the same we are going to use the same what, the same approach, like we need the non-y's and the non that is x's. So you are going to highlight the non-y's, okay, and then highlight what, the non-x's, and then you can see we are getting the same value as what, as this. And the all those three methods are driving us to the same what, are driving us to the same output. So majorly here, I just wanted to show you, you have very many that is approaches which you can use to get what, to get the same values. But it's always good to use this one, the that is the regression analysis using the analysis tool Prac. It is really presentable, and from it you can even drive that is more what, more or you can get more insights from, that is, from the analysis. And the advantage is that it will give you even the performance in terms of the model. Yes. Any question up to that point before